There's a number there. 12 right now. Yeah. And very well, welcome to week 8 Kahoot. Okay, so yeah, the answer is false. The reason is that the system believe that language is really the language in the use. So because books are static and it lacks interaction with other human or environment, so it's not language. So that's false. Okay, so Promptagator is dated by JC and showing surrounding words. Okay, we also see quite a bit entropy in the distribution. Yeah, so CMAO is the other way around. Using central surrounding words to predict the central word. Skip right is the answer, and very similar to CMAO, which is doing the max modeling, which is also important. GPT is not relevant because it is other. Okay. So we doesn't have changing beautiful. C. Very quick. Very quick. So very low entropy is and don't have changes in the beautiful. Okay. Mika. This modest now. So the correct answer should be retrieval filter and version filter. So as we can see in the picture here, right? So we can basically tell from the picture we are a good beyond that. Okay. So yeah, okay. If it is coming up in the first place and followed by Reformulation, John, Enhancement, and he's a table former. Bootstrap. Okay, the correct answer is everything is true. So I made it a little bit tricky because there are only three options here. And if others impression that not all of them correct, but actually everything is correct. So they're all the eval down in the table former. So the first two they are standard operation, and the final innovation evaluation set is the one eval innovated in the paper that combined the first two as caused by our lecture this week. Okay, so drug thing has begin their first case. Final question. Single syllable. I'm sure Dan is able to answer this question in flash speed. So the granularity is narrowed by the hop. So we can see from the figure here, right? So the zero hop means just the node itself. One hop means that it happens to this one other neighbor to hop to the two other neighbors. Okay, and yeah, the answer is the amount of hop. The podium. Okay, congratulations. Who is Dragon Pink? Could you please stand up?
Okay, let's start it. So I have one announcement. Development sprint 2 is finished already, right? It was last week for our speaker. So hopefully you've already turned in your slide deck for sprint 3. I think 3 groups have already done 2 out of our 6. So if not, please do it this week, because again, we can keep pace with respect to our schedule. And especially those of you who are in a CP 3106, 3108B, where you have 130 hours. Please schedule appropriately. One of the things that you can do to use up more hours is to go through the thin slides from other groups, okay, and check on their groups. You know, make a comment or two about how they're doing, because it will also help you get more knowledgeable about that. So spend an hour or two looking at all the other one. Okay, because this is pass-fail, it's just credits. You know, without a grade, we do that. So please spend the time supporting. Okay, I know for our undergraduate students and for many people with deadlines, very hard to make a lot of progress during the end of the year, because there are a lot of deliverables towards the end. That's very important. Okay, so without further ado, we will invite our presenters for W9, bootstrapping and iterative retrieval. So Vangmay, I think is presenting for himself. Yeah. Oh, I'll get the pen out. Sorry about that.
So hello everyone, I'm Vangmay. I'll be starting off today's session on bootstrapping and iterative retrieval. So over the last few weeks, we have looked at retrieval augmented generation, where a model just retrieves documents once and generates an answer. But today we'll move beyond this static setup, and we will look at how retrieval itself can become dynamic, reflective, and self-improving. So through the concepts known as iterative and bootstrap retrieval. So traditional RAG works like this: that there's an input query. That after the input query, we retrieve like top K documents, feed them to an LLM, and then use it to generate an answer. It is a very one-shot retrieval process. And it is a static approach which can lead to ambiguous user, which can lead to issues. Like the query might be ambiguous, the retrieval documents might be irrelevant, outdated, and the model has no way to correct itself. As shown in the survey paper, we now need systems that can reason, reflect, and adapt. So the major weaknesses of our one-shot method is that retrieval only happens once before reasoning, and generator cannot ask for more information. We need noise robustness, and that there is no mechanism for self-correction or self-checking. So consider this example. Which scientist discovered the element found in penicillin? So the ideal scenario would be to first identify what element is in penicillin, which is sulfur, and then find out who discovered sulfur. However, in a one-shot scenario, the retriever just fetches documents about the penicillin discovery, and it retrieves wrong context, and as a result, the content is hallucinated, or either something known as answer drift has occurred, where the answer has drifted from the original question. Next, imagine an ambiguous query. So, for example, when did he start the company? In this scenario, he might refer to someone mentioned earlier. Such queries are also known as unspecified queries and have some context that is missing. So the solution to this is query reformulation before retrieval. So approaches based on query reformulation are required to enrich such ambiguous questions with additional information to make such systems more robust. So for example, in the previous turn, someone asked, tell me about Elon Musk. And the current query is now, when did he start the company? So the company can be anything, PayPal or Tesla. So in this scenario, our system fails because it might guess that the user is asking Tesla, or it might guess the user is asking about PayPal, but the user might be asking about the other company. Then we are now suppose the retrieval has also succeeded syntactically, but the context may be messy. That might be because there are outdated or just or old documents that are present in the RAG. So in this scenario, generator has to again guess what the user wants. And this might again lead to hallucinations because there is no proper mechanism to evaluate whether the retrieval of a RAG system is correct or not. In this scenario, we need self-evaluation so that we can detect low confidence intervals, and being a corrective RAG / self-RAG system, which can re-retrieve or fall back to a better method like web search. So as we just saw that RAG collapses under multi-hop reasoning, ambiguity, and noisy or missing context. So we need systems that can firstly iterate, reformulate, re-retrieve, and bootstrap, which means learning from past retrievals to improve. So let's talk about what exactly is iterative retrieval. So this method happens in multiple steps and it is guided by reasoning. A strategy where the model performs multiple retrieval cycles and each are conditioned on evolving context. So suppose we ask the system which planet has the shortest day in the solar system and what causes it. The goal is to find two connected facts. Firstly, which planet has the shortest day and why it spins so fast. So in this scenario, as we can see on the figure, that firstly the retriever will get initial documents that mention shortest day and planets. Using that, it will come to the conclusion that okay, Jupiter has the shortest day, but none of the documents mention that why. So then we have a loop which will go back to the retrieval step with a new query. The new query would depend on a case-by-case basis. In this scenario, it would be about planetary formulation and angular momentum. Then the system will reformulate the query to ask that okay, why does Jupiter rotate so quickly? And then it will base its answer on the second iteration. Now let's talk about Bootstrap retrieval. In this system, we learn from the retriever's experience to improve over time. After many interactions, the model is able to use its own queries answers to generate new training data and update the retriever systematically. The most foundational paper of such system is called REN, which introduced the idea for using retrievers that are self-improving. The main idea was not only to treat the parameters of the model as knowledge, but also use a separate module that represents knowledge, which is essentially just a learnable retriever, and it enabled knowledge to be more dynamic in nature. So in step 1, we give an input with a mass token. So we retrieve candidate documents from a larger corpus. Then we feed the input and retrieve documents to the language model and predict the mass token. Now we measure the document. Now we measure how well the document helps the predictions. This is essentially your quality signal. Then in step 4, we pick documents that maximize this signal of quality and update the retriever just as we would do to our neural net model through gradient updates. So for example, I want to ask that, okay, capital of Paris is, and then mask it. The goal is to predict Paris. We retrieve candidate documents and combine the text with the query. Now suppose there's a document that helped to predict Paris. So that gets more signal. So now our retriever knows that in such similar queries, we need to retrieve this document. And if there's a document with a negative signal, the retriever would remember this next time and not output such documents. So the key observations over here are that the retriever is not fixed. It learns from its own outputs. It is a parametric method, and it improves iteratively without human supervision. The model effectively bootstraps its retrieval skill from self-supervised feedback. Here's a comparison of both methods. So iterative retrieval is non-parametric, while Bootstrap is parametric. Iterative retrieval works during the inference stage, while Bootstrap works on the training stage. So through iterative retrieval, we are able to improve factual accuracy and reasoning per query. While in Bootstrap, we treat the retriever as a knowledge base. For iterative retrieval, we get better answers now during the inference stage, while in Bootstrap retrieval, we get better retrieval next time. Think of iterative retrieval as a student double checking their answers before submission, and Bootstrap retrieval as a student analyzing past mistakes to study smarter. So here are the techniques that we'll be covering today. For iterative retrieval, we cover self-RAG, contextual query reformation, multi-op retrieval, after retrieval, and for Bootstrap, we talk about synthetic data augmentation and corrective RAG. So now I would like to call
Hello everyone, I'm on Zoom, so can you hear me?
Let us switch over to you.
Yes. Sure.
You can check it.
So you should see my screen now. Is everything okay?
Yeah. Okay, you can go ahead. Thank you so much.
Thanks. Hello everyone, I'm Ksenia. I'm going to talk about synthetic data augmentation for information retrieval. So first, let's just remind ourselves what is synthetic data augmentation. So it basically refers to using LLMs to generate artificial task-relevant data to either supplement or replace real training data. This approach is invaluable when the labeled data is scarce, when it's too expensive for us to annotate the data, and by producing extra training examples, LLM can boost model performance in low resource settings and reduce annotation costs. And in practice, synthetic data has improved NLP tasks, many NLP tasks like classification, question answering, and information retrieval as well. Though when we use synthetic data augmentation, it is important to perform some quality checks because generated data may contain factual errors or distributional shifts. So we need to filter the data to ensure that it's realistic and fair. So next, I will tell you about 3 very interesting papers that I found, and I will also mention their extensions at the end. So the first paper I want to discuss is called Document Expansion by Query Prediction, and it is known as DoctorQuery. So it was a pioneering effort in using generative models to improve document retrieval. They proposed to expand each document with predicted queries that the document could answer. A sequence-to-sequence model trained on query document pairs generates likely search queries for a given document, and these queries are just appended to the document text in the index. So this document expansion increases the chance of term overlap with user queries, addressing the problem of vocabulary mismatch. And the pipeline that I just described is on the right side of the slide. It's pretty simple. I also already talked about this one. So here is an example of query predictions on the dataset that they used, which is a mass marker dataset, comparing real queries. So for example, if we look at the first sample, input document describes the weather in Washington, and the predicted query is weather in Washington, DC. So makes sense. And the target query in the dataset is what is the temperature in Washington. And there are 2 more examples that show that yes, predicted queries are quite meaningful and can be useful to increase the overlap with the users' terms. So this paper is significant because it demonstrated that generating synthetic queries can effectively bootstrap retrieval systems by enriching the index, foreshadowing later works. So the next paper is InParase, data augmentation for information retrieval using LLMs. InParase introduced a fully unsupervised pipeline for creating information retrieval training data with LLMs. So specifically, the authors used GPT-3 to generate synthetic query passage pairs for a target corpus without any human labeled queries. The process involves prompting the LLM with a few examples and a passage from the target corpus to produce a plausible query that the passage can answer. These generated queries paired with their source passage form a synthetic training set that can be used to train a dense retriever. So here is the pipeline. They take from 2 to 8 examples from the dataset. They used a mass marker as well. They take a passage from the target dataset, and as output, they get several possible queries for this passage. So they tried to use 2 prompts for their few shot configuration. The prompt on the left only shows like document with relevant query, and prompt on the right shows document with a good question and a bad question. Here you can notice that relevant query is basically the same as the bad question in the second prompt. That's because they took relevant query from MS marker dataset, and for good question they asked people to manually create better queries for these documents. So the key findings of this work is that a dense retriever fine-tuned only on the LLM-generated dataset outperformed strong baselines like BM25, and even outperformed some self-supervised retrieval methods. This is notable because no real user queries were used. The LLM invented questions that made the retrieval to generalize well to the real data. When the synthetic data was combined with limited supervised data, which is line 16, the results in retriever showed improved zero-shot transfer to other tasks, beating models trained only on the original supervised data. So in other words, InParase synthetic queries helped the model generalize to new domains better than human data alone. And again, this paper demonstrated that LLMs can act as data generations, and it proposes a template for using LLMs to bootstrap retrievers in any domain without manual annotations. And then the last paper I want to discuss is Promptagator, few-shot dense retrieval from 8 examples. So they pushed the idea of synthetic information retrieval data generation further. And they showed that with only a handful of labeled examples, like from 2 to 8, they can use an LLM to produce a large synthetic training set for a new retrieval task. The idea behind their work is that retrieval tasks are not the same. Like as we can see in this scheme, they show that for MS marker dataset, which is the dataset for web search, the normal question is like surgeon salary per year. But there are other types of information retrieval, like if we look at fever, which is claim verification, there a query could look like music artist is a profession of Christina Aguilera's, and the retriever needs to find the information that will verify this claim. Same with there are 2 different tasks that we can see here, which is a Wikipedia entity, where the retriever is expected to just find all utterances of entity in Wikipedia, and Argo-ANA, which is counter-argument retrieval, where given a query, the retriever is expected to find arguments for the claim. So the workflow they propose is as follows. The first step is prompt-based query generation. We provide an LLM with a task description and a few example query document pairs, then ask it to generate many new queries for documents in the target corpus. The next step is consistency filtering. So what they do is they given the generated data from the first set, they train the preliminary retriever, and they check that the retriever retrieves the correct passage for queries generated. If it's not the case, then these are some noisy samples, and they just filter them out. And the last step is that they train a retrieval, but only with these filtered data. So they use only filtered synthetic query document pairs to train a dual encoder from scratch. Here are the results. So they showed that a few shot prompted LLM can yield retrievers that match or even beat fully supervised ones. In experience on these 11 BEIR data benchmark tasks, a retriever that was trained on Promptagator's synthetic data outperformed models trained on massive human labeled datasets. For example, we can see that it beat strong baselines such like Colbert version 2 and Splade version 2 that had used 500K real queries for training. This was achieved with only, say, 8 seed examples. So it highlights the power of LLM generalization in this case. And the synthetic trained retrievers, when followed by a re-ranker, achieved state-of-the-art results on many tasks. So, like, very successful results. And the method also emphasized that robust prompt design and with automatic filtering can result in such high quality data. These are just an additional papers that can be interesting to look at. The first one is about SWIM-IR. So it basically extends the synthetic augmentation to multilingual and low-resource languages. The authors use an LLM with a summarize then ask prompting strategy to generate queries in 33 languages using a summary of a document to help the LLM to form an informative query in the target language. The resulting synthetic data set enabled training a multilingual retriever, competitive again with human supervised models. The next interesting work is Converser. So it adapts the few-shot synthetic approach to conversational search tasks. They built their work on InParase and Promptagator. They generate multi-turn conversational queries and answers using only a few example dialogues. So the LLM is prompted to produce a sequence of related questions, simulating a conversation for a given text. With just 6 example dialogues, the authors were able to train a conversational dense retriever that matched the performance of models trained on real dialogues. And the last work is InParase Plus, which is a very recent follow-up to InParase that supercharges synthetic data generation. So they introduced 2 improvements to InParse. The first one is that they fine-tuned an LLM query generator via a reward signal to produce higher quality queries. And they used chain of thought prompting to generate more thoughtful queries. These techniques reduced the need for aggressive filtering of generated queries while further improving the accuracy. So that's it for me. Thank you.
Thanks, Stephen. Let's ask the floor for any questions. So we don't have a discussion catalyst today, even though we have a lot of people assigned to this work. So I would try my best to do it on the fly. But first, I want to prompt you guys for questions. Can anyone help to summarize, synthetically data generate a summary of Ksenia's presentation? What's the key messages that we're getting from this synthetic query generation part? I hope you are all doing homework for other courses while listening to the presentation. So can we go back to the beginning of your slides? Okay.
Mhm.
All right. So when we think about synthetic data generation, and right, what we are trying to do is use an idea that comes with IR. Okay, IR as information retrieval. We have our course on it, right? And usually when we think about probabilistic information retrieval, which was the paradigm before we come to RAG, okay, what we are doing is thinking of a document as something that is begging a question. So when you go to Ksenia's other slide, I think 2 slides down or so, yeah, to DoctorQuery, right? So she wrote on this slide here, table 2, from that paper, is the idea that you have documents, right? And you are looking to figure out what type of query does that document want to find, right? Why would we do that? Right? Usually we want to go in the other direction, right? You have a query and you want to find a document. Okay, right? So this is sort of flipping it on its head, right? You're saying you're a query, you're a document. What type of queries do you answer? Right? And in a lot of IR formats, people will tell you, if you go to the reference library in NUS, say, oh, can you imagine what type of document that you're looking for? And then figure out what keywords are in that document. Okay, and then query your system for those. Right. So you imagine what types of words are in the document. That's sort of like what we're doing here. Right? We're flipping the document and saying, okay, imagine we have this document. What words does it contain? Those are the words you want to search. Right? So that's what it's saying here. So in some ways, when we think about LLMs, there have been studies to say, you know, maybe certain pieces of information that the LLM has ingested are actually not retrievable anymore because they've been overshadowed by other queries that you would normally think of when ingesting this information, right? So you can think of all those unloved library books sitting in the stacks, 30 years, musty smell, etc. Like they're not findable anymore, right? Nobody goes down there, right? Because all those documents, they're not being served. Okay. So when we think about DoctorQuery, that's a very good idea to come up with, you know, to say, when I look at it in the document, what are the questions they can answer? What can we retrieve?
Yeah, and what the authors have also mentioned is that providing a document, trying to like augment the document, not the query, allows the model to see more context and to think of like better ways of like it can output more ways of formulating the query than just if we asked it to augment the query itself.
Yeah, I think that's a really good point. So I'd like you to see both of these paradigms as separate ways of thinking about the document query relationship. Okay, usually in IR, we're thinking a query is looking for a document. So I think, you know, what is the relevance of this query to a particular potential document? That's scored high, I want to bring it up. Okay, and And what we're doing on this side is doing the flip side, right? We're considering a document saying, what queries could it satisfy? And I want to bring those queries up to the forefront, right? So you can meet halfway in the middle. You can say, I have a hybrid that considers both sides of the coin, right? And how would you build that system? So if you have ideas for that, you can write it in Slack. Yeah, I'll try to write this down later for you guys to have a discussion about. Okay. So oftentimes you want to think of the query and the document as surrogates for each other. In fact, we are constantly, whenever we use search engines, now ChatGPT, offering new documents every day. Those documents are extremely short. They're called queries, right? So by building lots of these small documents and then looking at what they retrieve, they're basically summaries, right? Your query is a summary of a document, right? Because you click on that document, that means it's a summary. It's what you want from that document. So in many ways, you can look at this paradigm and say summarization and information retrieval are intimately connected to each other. Okay.
Sorry, just
Yeah,
one
go ahead,
question.
Jonathan.
It's like a really like a summarization of some knowledge point, like example, grammar exam. And the tricky part is actually there could be multiple knowledge point in the phrase lines.
Right. So the question Jonathan asked is like, there are multiple points that are in a document, right? Like these documents that Ksenia has on her screen, right? There's some predicted queries, but you can imagine some other ones, right? So which ones are the right ones? That's sort of a summarization problem, right? Because many times when you're doing a summary, there's more than one thing that can be summarized. You have to decide what is important, right? So how would you do that? I mean, you talked about TF-IDF and other types of scoring systems that show you what's semantically important within a document, right? You can imagine how they apply here. There's also other things that we had talked about in previous things. Like last week, I think we talked about chunking, right? So in chunking, we also say, okay, maybe things that are lower down in some type of tree structure may be less relevant, right? Or things at the top of the document or title of the document, they're more important, right? So we have to be able to prioritize what is important in the document. So those are good points that John brought up. Ksenia, do you have anything you'd like to add for DoctorQuery or for any of the other papers that you looked at?
Yeah, I just want to add to that regarding the last question. I think that Promptagator is like they are trying to solve this task of diversifying the queries that can be generated by manually developing these 8 examples that they provide to the model. I think that prompting can be like one part of the solution if we want to output as different queries as possible.
Perfect. So Ksenia is also pointing out one other attribute which features in the works that she looked at, like the Promptagator, right? Which is the idea of contrastive or diverse information, right? So you have a document, you want to try to find out as many different types of information you need that it satisfy, right? You can also marry that with a contrastive approach, which is one of the other papers, I think the InParase paper, where the idea is let's look at good queries and bad queries for the document, and then pull more towards the good queries, right? So that you can highlight, even from a diverse data set, which ones are the more likely queries that we're going to retrieve the document. Any other questions or things that people want to bring up? Hi, Tao, or anyone else online?
Yes, I am. Thank you very much. So, based on the current panel, I'd like to see that, for example, for the synthesis data generation, or even the very traditional, like pseudo document generation. So maybe we can use the term like augmentation. I mean, to some extent, this expressions or these concepts are well correlated. So I'd like to say that. Another way to understand these techniques, like a document to query, I mean, it can be seen as a kind of augmentation. So these works are very related to RAG.
Right.
That's what I'd like to mention.
It's definitely pointing out, again, the synergy that we highlighted earlier, that, usually you think about retrieval as one direction, right? But here we're flipping it on its head, right? We're saying that the document generates queries. You can know which queries are better than others, just like we usually think about ranking documents in Google or Baidu, right, as to their fitness or query. We can also do it the other way around, right? And just like in document retrieval, when you build the search engine result page, SERP, right, you want to show 10 search results. You want those 10 results to be sort of diverse from each other. They don't want to be all 10 copies of the Wikipedia page, right? That would be a waste of space. So the same is true of the generated queries. We want to generate queries that are diverse. Okay. So with that, let's thank Ksenia for her presentation.
Thank you.
And we'll move on to Yiqi. So I think Yiqi is online already. Yiqi, you're muted.
Okay, I'm online, and I will share my screen.
All right, great. You can take the floor whenever you're ready.
Okay. So can you see the screen?
Yep, we can.
Okay. Okay. Now I will introduce these two papers, Corrective RAG and self-RAG. And actually, these two papers are the idea of these two papers are quite similar. So it's really a good idea to put these two papers into one topic. And actually the idea of this both paper is to reflect the search result using the search engine before generation, and we can reflect whether the retrieved result is correct or not, or whether the search result is relevant to the question, and then to make our generation more correct. Then let me introduce the basic idea of the corrective RAG. Actually, the traditional RAG is not good enough because it's highly different the retrieval quality. So corrective RAG introduced a lightweight and plug-and-play module to reflect the result. It is a plug-and-play module, so we can use it or use a different module. Maybe with a higher performance or maybe different mechanism. So it is a plug-and-play module. And actually the corrective the self way and the idea of self-RAG is to judge whether the document is relevant, and the corrective RAG is to use a retrieval evaluator to judge whether the retrieved document is correct, ambiguous, or incorrect. You can look at this diagram. In the retriever, there's a prompt says who was the screenwriter of maybe the book or movie, and it will retrieve some results, and the evaluator will evaluate the results. If it's correct, and it will decompose this trunk into the much smaller chunk, and to filter the most relevant stripe, and then compose into a result. But if it is ambiguous or incorrect, maybe it will, if it's incorrect, it will rewrite the prompt to search again, and if it's ambiguous, and it will both do the two-way approach. They rewrite and search again, and they use and they decompose and recompose the information of this search term. After the evaluation, the question that combine together to fit into the generator. And so if you can see if it is correct, and we directly use the recomposed result. If it is incorrect, we use the search result after rewriting the searching prompt, and we combine them together. So that's the basic idea of the corrective RAG. So if it's incorrect, we correct it. Okay, and then the pipeline of the corrective RAG algorithm is like this. So it calculates a score of confidence. So it based on the score of confidence to judge whether it is correct or incorrect or ambiguous. So it has a threshold and use the score to judge it. And so how to train corrective RAG? And the corrective RAG uses a very lightweight model. It is used T5, and the parameter it is it's smaller than 1 billion parameters, and it uses fine-tune evaluator, and it is trained on the PopQA dataset. And let me be much more clear, introduce much more clearly about the data. And actually, there is a golden subject wiki title provided by the PopQA dataset, and the corrective RAG just trained with this data and fine-tune a model named T5, and with a parameter less than 1 billion. And how this paper trained the retrieve evaluator. Okay, and the result of PopQA is achieved 61.8, and actually it is trained on PopQA, but when using different benchmark or different dataset to evaluate it, you can see it generalized quite well. So it's not only perform good at the PopQA benchmark, but also perform well at different benchmark. Okay, and then let me introduce it is a paper with very similar approach. And it addresses similar issues with the corrective RAG, and is to retrieve and reflect. So this is the pipeline of the self-RAG, and when receive a prompt, and he will receive and judge every search result to see whether it is relevant or irrelevant or partially relevant, and sort the confidence by this three tag, and then use the most relevant results to generate the answer. There are three different types of the retriever is ref, is support or is use, and which means evaluate whether they are relevant or whether they are support or whether they are useful or not. Okay, and this are used in the algorithm. And how to train the self-reg? Well, this is much different with the corrective RAG because corrective use a direct train on the small subset on the PopQA. The self-reg it shows my network are not so stable, so can you hear me? Okay, and then let me introduce but the self-reg use a different approach. They use reflection tokens generated by GPT-4 too, and without any manually labeling. So actually, it somehow distill a part of the GPT-4 to learn from the data that GPT-4 output, and then use this label to train the evaluator of self-RAG. Okay. And the result is okay, and the result is also it generalizes very well across different benchmark. Okay, and that's my presentation to introduce these two papers with similar ideas.
Okay, let's thank Yiqi for their presentation. So as I noted, we actually have covered RAG and I think part of self-RAG, if not otherwise before in week 7. So hopefully this is familiar material to you as it was presented. So there are some discussion questions that I think Rishad was online previously also offered. So I'll just narrate this query again. Systems like Corrective RAG and Layer, which is another paper that was gone over in week 7, have a built-in evaluator or competence checker to judge the information they find before giving an answer. This is like AI vetting AI, right? So own self check oneself or whatever it was the minister said, right? What are the risks if we build an AI that becomes very competent? We went over the answer in class. Do you guys remember what we said? Model collapse. So Amanda said model collapse. So we've gone over this before, right? It means that the logics of the AI get overconfident, right? And they start spewing out the same results all the time. So if it gets too polar, it doesn't have enough diversity in its answering, and it stops being a very useful validator. So to stop that problem, what types of things can we do to combat? Anyone would like to try? Yiqi, do you have an idea of how we would combat model collapse? We were overtraining or overutilizing an AI model to do validation. Go ahead.
I think like last week or previously, like we alluded to some things that we can do, like for example, dropouts or having like mixture of experts that deal with different things. Yeah. Okay. Yeah. So interest, right? Go ahead. I forgot your name again.
I guess like use it discussed last week. Like having a separate model so that it is like sampling from different machines.
Right, so you want checks and balances, right? Otherwise, you end up with a system that self-validates and it's out of tune with reality, right? So either we do things like sparsify a model using dropout or other things, or using a mixture of experts, or we could do Aaron, right? I've got your name.
Oh, sorry.
Your name is
Zach.
Zach. All right, Zach said to use a separate validation model that's not in being tuned on the results, right? So that's the normal test and training separation. So if you do have time, you can answer the questions that are on. Okay. Do you have any points that you'd like to ask or volunteer? Or should we go ahead?
Thank you. So yeah, yes, I have one point to emphasize. For example, given the introduction about corrective RAG and self-RAG, right? I mean, within the original paper, like they develop some way to quantify the confidence or the evaluator, right? So in fact, it can go beyond that. For example, like the factor diversity can also be associated with the confidence or more other factors. So the original paper may just focus on something. In fact, these ideas can be further extended with many other factors: diversity, noise level, duplicate cases, or many more other factors. So I'd like to point out that. Thank you.
Okay, so I think we should take a break, right? So why don't we take a 3-minute break and come back after you get some water? That's great. We'll have our next session.
It was just the plan. Actually, we need.
Yes, I think 1%.
Because this would be. So now. That's not. But I get loans. But not added for acceleration. Yes, man.
Okay, I think we'll get started again. So I think our next section is given by Ada. So Ada is coming.
So are we talking about query reformulation, which is essentially expanding statutory writing the input query to the retrieval system to make it friendly for the retrieval system?
Yeah, you have to click on the screen and it'll start.
Right, so the central example which is that to reformulation is that users are kind of bad at phrasing their query sometimes. So you have misspellings, you have like misuses of synonyms, things like that. So if your query is bad, chances are your retrieval results are going to be bad, which is especially true for retrieval systems that aren't that smart. For instance, things like BM25, you try to look for exact word matches. So if you misspell a word that is a very important word, such as like twin bed versus twin feet, you just get completely unrelated. Yeah. And another problem is that different terms may have the same meaning. This is known as synonymy. And so if you search for one term without necessarily searching for other documents that contain terms that mean the same thing, you may fail to retrieve all documents that are relevant. And this reduces, sorry, these are the wrong amount. This reduces your recall. Yeah. And another problem is polysemy, which is that same term in multiple meanings. So if you search for one term, if you search for one term with multiple meanings, you may retrieve multiple documents which contain that same term used in different contexts, but only a subset of those retrieved documents. And so this will decrease your precision. So the solution to this is to change the query to be friendlier to your information retrieval system. So there are two types of query reformulation. The first is query expansion, where we add terms to the query to aid the downstream retrieval system in finding things that might be related but not mentioned using the exact language that the user used. So the first one is lexical expansion, where we add terms into the same thing. And the other is knowledge expansion, where you try to infer user intent and add terms that align with that intent. So we have some examples here. And lexical expansion tends to improve recall, because if your query terms are connected by a logical OR, then your new retrieved document set is strictly a superset of your old retrieved document set. So your recall is going to go up. And knowledge expansion typically tries to improve precision by narrowing down documents by user intent. So the last one that is more relevant to, I guess, search engines such as Google is signal-based expansion, which has a couple of different subtypes. The first being click signals, for instance, to append similar queries from other users. And another one is filter signals, which filter retrieval results by metadata about the query. So if you know a user is in Singapore, you might try to return results that are more relevant to that information. So the second type of query reformulation is query rewriting. The most rudimentary type consists is normalization, where you check spelling errors, you reduce all words to their stems, etc. And the more interesting types are the generative methods and the iterative methods. So generative methods treat a sequence model to rewrite the query, while interactive rewriting, especially relevant for computational systems, asks user to explain the query further if the original query was determined by the system to be. So I guess the most basic query expansion method in literature would probably be the ROQL, which operates within the vector space model of information retrieval, where queries of documents are represented by vectors in convention. So given an initial query and a set of relevant documents and a set of irrelevant documents, what this algorithm tries to do is to push the query towards the vectors for the relevant document, while pushing it away from the vectors for the irrelevant. So as you can see here, we linked the original query term and the relevant document and the irrelevant document by 3 different constant parameters. And when you iterate this formula, your query, your queue is going to go closer to the mean of the set of relevant documents, while going away from the mean of the set of irrelevant documents. So next we have RLM and RPE. So the authors of this paper realized that the word embeddings of the time, so like rough and word to better, were kind of suboptimal for information retrieval, because under these word embedding methods, terms with opposite meanings could appear in similar content, and so they would be close together in the embedding space. But when you substitute one for the other, it completely changes the query meaning to perhaps its opposite, and that is not what you want for information retrieval, because the transform query should retain the usage. And so they train a new set of embedding models to maximize the downstream retrieval accuracy. So they introduced 2 methods of doing this. So one of RLM, the other of RLM. So the first one minimizes the cross entropy between the predicted and actual probabilities that a certain document is relevant to the query. Might be a bit hard to see the cross entropy formulation here, but if you just take a look, and the probability of a word being relevant to the query is taken by a simple subgroup. And RPE in contrast uses logistic regression to model binary classification of documents, of words, of terms into relevant or irrelevant. So once they calculate this probability, they maximize the log likelihood over both the sets of positive terms and negative terms, here denoted H1 plus and H1. And for the negative samples, they don't want the words to correspond to any actual words, because negative binding is kind of hard. So they simply draw it from Gaussian noise. So the RPE model doesn't actually directly give a language model of the probability of the word given the query. So instead of doing this, after they train the model, they derive the word embedding vectors from one of the hidden layers and dot product with each other as a similarity measure, and use this to calculate the relevance probability. And so once they get these probabilities of word relevance, they linearly interpolate in a baseline maximum likelihood model, and then use it to predict the top K terms that should be added to the queries. And after this, they add top K terms to the query and rerun it, the retrieval with the new query for evaluation. And so this being a relatively old paper from 2017, the comparisons, the baselines used aren't exactly state of the art, but it's clear that they did quite well with what they had. So outperformed basically all the word embedding baseline at the time. So for a newer method, GenPRF and GenQR are LLM-based models for query and expansion. And so given a query, the GenPRF retrieves a set of documents using the original query and concatenates all documents to the query in the prompt used for query expansion. And so you ask the model to expand your query given documents that were retrieved from the original query. And then once the model returns you the new query, you use that to query the actual information retrieval system instead. So for the instruction tune model, they use a slightly more detailed prompt. And because they found it quite hard to apply label data sets for this, because nobody really makes data sets for query expansion, they derived their own weakly supervised data set instead by taking existing information retrieval data sets and finding query pairs that are similar in that they share many of the top tier retrieve documents. Then after that, they try to find which query is more effective. So they use that as a query, as a ground truth query to work with. And they also remove stop words, so words that are mutual in meaning and presumably unimportant, such as is and as. So after they filter the set through these three methods, they use it as training data. And they find that generally all of their filters help. They do an innovation study on their filters, and they find that using all three filters on the training data gives the best retrieval performance relative to ablating one or two or all. And so GenQR, as opposed to GenPR, propose query rewriting instead of query expansion. They use the same model architectures with the same training procedures, but with different prompts, excluding the retrieve document set DI. And they find that the additional context given to GenPR doesn't necessarily help on all data sets. And on the one data set where it does help, the instruction tune model benefits more than the non-instruction tune model, which might provide an indication as to which kind of models you might want to use for query finding. Yeah. So now we move on from query extension to query rewriting, which doesn't necessarily have to retain all of the original query. So involved in for query rewriting, the model is allowed to change the wording of the query entirely, as long as it maintains the original user intent. So a paper from 2017 uses reinforcement learning for query rewriting. First, they process the original query by a model, and they also feed the candidate expansion term vectors into another model, and then they calculate the probability of adding the adding term as this. Yeah, and the rewritten query is the concatenation of all the term vectors for which the probability that it should be included exceeds some two thresholds. They also explored an alternative method where RNN is used to generate new query token by token. So they define the probability distribution by taking softmax and decode this by basically spinning a dial on probability distribution for each token until it's less subtle. In practice, rather than using a vanilla RNN, the author uses LSTM instead because it generally has long-term dependencies better due to the presence of scaling. And so as for the actual RL part of this paper, they train both models by the reinforced algorithm, which seeks to improve upon the baseline reward value as much as possible without straying too far from the original policy. So your basic reward is basically a reward on uniform distribution of selected terms. And what this represents is the random chance result that you want to improve. And surprisingly, they managed to outperform even supervised learning methods using RL. So lastly, we have a conversational IR system query rewriting method called Chien. So the conversation may essentially be defined as a sequence of tuples of user queries. And so at the end of this one step, you want to find a set of passages that are relevant to the history and the user's current query, which will be used to generate the next. Yeah, so commonly you first need to formulate a query to an external search engine or some other IR system. And the method for formulating this query is to concatenate the history and the current user prompt, the current user query, together with the prompt to an LLM that asks it to give you a good query to ask the IR system. So Chien uses 5 approaches to rewrite the LLM input so you can get a better query. First, you clarify the question. Second, you expand the response. 3, you predict a potential response and run that potential response by the IR system and use it to expand your input. And then fourth, you detect you look for a switching topic because not all the conversation history might be relevant. And you also attempt to summarize the history. So the authors combine the above 5 approaches in the following ways. First method they call ad hoc. So if there was a topic switch, you use all your methods except history summary, and if not, you use everything. And the second is by fine-tuning the LLM on an augmented data set, where you try to move it towards the query you would have produced had it had access to the correct document that you wanted to retrieve. So the authors find that cheap outperforms competitors on both fast and dense retrieval by large margins, especially for conversational IR systems that just take the history as it's without rewriting.
Okay, check our speaker. Any questions? I'd like us to go back a couple slides and sliding. And I just want you to ask yourself which of those strategies that data presented from the Chick paper would work better and why. So just do some simulation in your head. Pick the document or query or both. Then play it out in your head. And then give me an answer. I've written it on the slide. You don't have to answer it now, but it's also something I would like all of you to train yourself to think, right? Because often we go to the results of a paper and we say, oh, it works really well. But again, like I've said several times in our lecture, if you want to develop intuition, you can do that. I mean, you can play thought experiments all the time. So question disambiguation, rewrite the query to be less ambiguous, right? By giving a new version. Expansion to add more details to the recent response. You ask an LLM to hallucinate, if you will, more details that aren't there in the original response. Pseudo response to predict a potential response before sending it to get and expanded details. Right. Topic switch, which says take parts of the history and throw it away, and then generate something. So if you think about that, it's a little bit related to like interest point about dropout, right? Just take some part of it and mask it away, and then you see what you generate different. In history summary, right? So history summary again is about saliency. Out of all the history, which parts of the history are important, right? So don't answer it now if you don't want, but I'm curious if anyone wants to spend a couple minutes giving an answer. That would be great. I thought, do you have any comments before I conclude about that?
Thank you. Maybe a quick comment is, I mean, given the need or this importance of query writing, I mean, there should be multi ways to do that. From the way of, I mean, from the view of adopted machine learning method, we may train different like classifiers, or we can also use reinforcement-based methods. So there will be different choices leading to different performance. So yeah, that's a point to take into account when we solve this kind of problems. Thank you.
Haikal reminded me, you know, if you don't know the reinforcement learning terminology, it'd be very hard to decipher. They're very easy concepts, but unfortunately, it's sort of clouded by a lot of terminology. We don't have the time to cover it today, but I think among the graduate students or people who are in masters, they may have had some exposure. Okay, so if you don't know reinforcement learning, don't worry about it. can revise it on your own time when you have a bit more time. I know for many of us in undergraduate won't have the time now. I can think about it. Okay, I think Xinpeng is next. Xinpeng, are you there?
Yeah, I'm on that.
Okay, let's give you a screen share. And you can share screen. So if you care, please do answer questions that I pose.
Can you see my screen?
Yes, we can.
Hi, everyone. In the next few minutes, I will explain how RAG can be used to solve complex multi-hop queries. I will start by showing why the classic one-shot retrieval struggle with these problems. And then I will introduce two representative in iterative retrieval methods, IRCOT and self-ask. And I will finish by discussing the main challenge they share. Let's look at a motivating example. Who was president of the U.S. after the dissolution of the Soviet Union? A one-shot retriever simply searches using the original question, but that's a problem. Without first establishing when the Soviet Union dissolved, it's very hard to get the right answer. That's important facts like the dates are often scattered across different documents, so they rarely appear together in a single passage. In this case, a one-shot search may return a document that only tell us who was the president at that moment the Soviet Union dissolved. It will give the wrong answer, such as George Bush. By contrast, if we can use a iterative approach, we can first retrieve the dissolution date, and then we can use that date to perform a second retrieval to find who wins the election after that event. And it will correctly lead us to the Bill Clinton. Now I will introduce two iterative approaches. The first is IRCOT. It stands for interleaving retrieval with chain of thought reasoning. The main goal of IRCOT is to create multiple interleaved interactions between retrieval and generation. In other words, retrieval some evidence and use that evidence to produce an intermediate reasoning step. Then you can retrieval again by that reasoning and repeat until we got the final answer. IRCOT work like this. First, it will start by retrieving key documents and use the original question. Second, it conditions the generator on three things: the original question, the retrieved document, and any previously produced chain of thought sentence. And it will also ask it to generate the next COT sentence. That COT sentence should tell the retriever what fact to look for next. Third, we can use that COT sentence as a retrieval query and add the newly retrieved results into the context. And then we need to go back to step 2. Finally, we will repeat step 2 and 3 until the generator's COT sentence contains the final answer. For example, it will write, so the final answer is, or until you hit a preset maximum number of retrieval steps. Here is an example. Who wrote the 1970 international hit song that Mary Hid is most recognized for? The first retrieval, we can uncover the song title, and we can call it intermediate fact T1. And then we can use T1 in a second retrieval. That's the songwriter's name. It's T2. With T1, T2 as intermediate reasoning steps, the generator can produce the final answer. That stepwise recovery of missing facts is the core stress of IRCOT. Empirically, we can see a consistent pattern. Without retrieval, large language model often lack of factual knowledge to answer correctly, so the answer is all wrong. At one shot, retrieval recovers some key facts, but it's often incomplete, so the answer may be partly correct. IRCOT's iterative loop recovers the missing intermediate facts and produce fully correct answer more often. Quantitatively, IRCOT's biggest gains appear in recall. It also generalizes better on out of distribution setting, or you can also it also shows stronger performance even with smaller models. The second approach it will cover is self-ask. Self-ask takes a different angle. Instead of pilot interleaving retrieval with COT sentence, it actively decomposes a complex multi-hop question into a series of simpler and single-hop sub-questions. Then retrieves answers for each sub-question. As shown in the right, with model-generated text shown in the green. In self-ask workflow, we first use a few-shot prompt to ask the model whether further sub-questions are needed. If so, the model generates a concrete follow-up single-hop question. The retriever then searches for the answer to that follow-up question and inserts the retrieval response back into the prompt to generate the next follow-up question. This process repeats until the generator outputs a concluding process, such as so that the final answer is. In short, self-ask modularizes the reasoning process. It breaks the complex question into small and single hop pieces, and then solve each pieces by retrieval and then aggregate the results. When combined with a search engine, self-ask shows significant improvements on metrics like exact match and F1. Although iterative retrieval methods like IRCOT and self-ask improve performance, they also bring some new challenges. The single most critical issue is when should we stop iterating? Adding more retrieval steps can help accuracy. At each retrieval appends more text to the context, so it will increase the demands on the generators. It will ask LLM to have more or have stronger long context understanding and reasoning ability, and it also will raise latency and computing cost because each additional step will require both retrieval call and extra model inference. One promising solution is adaptive RAG, which dynamic decide whether to continue retrievaling or we should to stop. Chien Hao will introduce adaptive RAG next. There are also some additional related papers. I list there in this page. If you're interested about it, you can visit the link showed in this slide.
Okay, let's check our speaker. So I posted some questions that came from Claude on the paper. So to take a look at the ranking questions that I put up about the Xinpeng extension. Again, you may recall that some of these models that have gone that we are discussing today on iterative retrieval sound very familiar because we did cover some of the same technologies earlier in week 7. Okay, so do we have any questions from anyone about what was presented about the self-rag and also the ask self and the higher cost interleave chain of thought, retrieval and chain of thought. Any questions online? Online is pretty quiet today, except I Alice always there to give some answers or some thoughts and discussions. One part we did cover a little bit in week 7 that we haven't covered today is again about efficiency, right? There is a lot of rollouts and extra computation we have to do to interact with iterative work, right? So a lot of times we're doing this behind the scenes. Like actually when we query Google, they have been doing quite a lot of work since the 1990s to take your one search query and actually execute query expansion on the back end and query their own system around 20 times per year. So when they do the expansion, they carry out 20 searches, they unify all of those when they give you the search results. And so there's a lot of efficiency that has to be done in order for that to happen in the millisecond times that it does produce results. And so they have multiple servers, they cache things, parallel. You can expect this type of computation is also being done now. In GPT-5, as we already know, it's a rally mechanism, but has the sort of like mixture of experts type of thing built into it. So they're relearning or trying to re-implement some of the things that search and technology has had. But definitely the computational costs are very heavy right now on many computers too. Reasoning plus retrieval system. If there are no comments, I think maybe we'll go on to the next section. So you can stop your screen share.
Yeah.
Thanks so much.
There's a question.
There's a question from Taka, I think. So let's read it out. Taka, are you there? Do you want to speak your question? Okay. So Taka says, I have a question about IRCOT. I think the data catalog information, such as the catalog of all available documents via RAG, should be injected into a prompt to generate follow-up queries to determine what to do next. So maybe we can ask Xinpeng whether he has any opinions about the query, which is on the Zoom chat. Otherwise, we can also try to answer that question ourselves. Oh, sorry, you're muted. while Chien is thinking about this, does anyone have an opinion about this? This is more like a method for injecting an index, right? You're saying I have an index of all the documents, right? Data catalog, as Papa is saying. And I want to inject the index as context history before giving the information. Okay, so if you take our IR courses, 3245, one of the key things we do in IR is to build an index, right? So if you think about a book, right, the book at the end of a book, many times a textbook will have an index, right? And so that's what we are trying to use to make the retrieval of documents fast, right? Because when you look at an index, you have to do sort of summarization as well, right? Again, what we talked about earlier is you think about the passage and then you say, what keywords are there? You take these keywords and you build the back of the book index to say which page is it on, right? So the page number corresponds like to a URL, right? So I can get the document that, right? So if we were to build an index and then provide it, let's say you took the book, a book, okay, like a textbook, and you chop off the back spine and you add that as context to an LLM, and it produce better results as a result of it. What do you guys think?
Chop off the back spine meaning.
I mean, like you just take the part of the book that says index, right? It has like terms for A all the way to Z, plus the page number, right? And you don't have to use the page number. You can just think of like having a Google index which says this term is present on this web page, right? Indra?
What if I say no? Because like for example, in IR, when you have indexes, the reason it works well is because like, I don't know, if you take like a B tree or something, it splits the search space. And then like the part of the index that where it matches, it just looks at that. But the way that language models work, and if it's in the context, like based on attention, it has to like still look at everything. So that's why it may not do the same kind of narrowing like a B tree would. So that's my argument for why not.
Someone from Zoom says go ahead.
Okay, Shimal, do you want to Narang? Sorry, I'm not sure which one I should give it name.
So I wanted to answer the question asked by Taka. So in the paper, the approach that they use is that once they start with the basic retrieval for the question that we give, and then they try to get a reasoning step. So based on the reasoning step, they use the reasoning step as a new query, and that new query is used to retrieve additional documents. This basically adds more context, and this is repeated multiple times so that we can get the most accurate answer. So it's basically a chain of thought kind of reasoning that goes on, and each reasoning step is in turn used to retrieve additional documents, which can later be used to improve the answer that the model gives. That's my understanding of what approach is being used in that paper.
Right, that's what's being done in the IR paper. Yeah.
Yeah, thank you so much for elaborating on it. Yes, yeah, that makes sense. Yeah, I was just thinking whether like yeah, if you have a kind of a catalog of available document, and if we can tell LLM that we have this kind of documents, then maybe LLM can create a more efficient or effective like a queries based on that. But at the same time, I understand. Yeah, this could be challenging. If we have so many documents in the catalog, maybe it's not realistic to inject this kind of information into the prompt, given the context size constraints. But yeah, thank you for the discussion.
Okay, going back to our first two lectures when Prof. Miao was telling us about generative information retrieval, right? This is similar, right? This is saying, you give the LLM the index, and then the LLM will be the one telling you which documents are relevant, right? Traditionally, we don't do that, right? We go to a search engine, and then we let the search engine tell us one, right? So the flip side of that is like generative information retrieval. We just give all the documents to the LLM, and then we ask LLM a question, and then it spits out an answer. So in some sense, all the documents are being sort of like pseudo-ranked in the LLM's brain, if you will, to give an answer, right? Because it's doing all the relevance assessment and then using next token prediction to generate a document, right? So they're complementary approaches. So yeah, it's not to say that this approach might not work, but it definitely has a different flavor to it. So you can think about this in relation to generative information retrieval, as Miao mentioned in the second lecture. I wonder if you have any other input on that.
I'm fine by now. Thank you.
Okay.
Mm.
All right, so let's go to our next presenter.
And now I'll be talking about adaptive RAG. So the problems of traditional RAG, as mentioned in the previous few slides before essentially, if you always have if a language model always does, let's say, one single hop RAG retrieval, then for simple queries which are stored in maybe the LLM kernel default neural weights, for simple queries like that, it actually does not need to do one retrieval, but if we naively just do one retrieval all the time, then it could waste resources. And for queries that require multiple steps, as mentioned previously as well, this one retrieval will not work well. So adaptive RAG solves this problem by training essentially a classifier. So in contrast with previous methods where maybe they try to reformulate a query, in contrast with previous methods where they do other stuff, adaptive RAG trains a classifier to say, given a query, how many hops do we need to do to how many hops do we need to retrieve the RAG from? So like it kind of predicts ahead of time. You try to train a classifier to predict ahead of time how many hops we need. And it can be implemented in multiple LLM infrastructure or frameworks like landscape. And so essentially the key problem about training such a classifier is that there's usually at least the paper that they covered over here, this paper, the key problem is that there's not an available data set saying, hey, this query requires how many hops, this query requires how many hops. So they needed to use a technical and silver labels to train the classifier instead. So the key idea here is that in the absence of such a direct data set, you can train a classifier in the following way. So you start from a query, and so you have data sets of queries and answers, and these data sets can either be single hop or multiple hop. And you want to use these data sets to kind of train number of hops predictor. So the idea is that you give a large language model these data sets and you make it try all possible options. So you make it try 0 hops, 1 hop, 2 hop, 3 hop. Make it try all possible number of hops that you're interested in. And then so each configuration will give you a certain answer, and you score the answers against this data set. So it's kind of like an indirect way of if I would give an analogy, instead of telling the child, hey, this query needs this many hops, this needs this many hops. You tell the child, you go try everything, and then based on the child's answer, when you try every single method possible, you tell it, hey, this method actually works the best. and from that you can learn indirectly the number of hops. So yeah. So actually that's the key idea of this paper. And so here are the results that they presented. And essentially the key results shown here is just that the key results just that adaptive rec works. It's kind of like it balances the time required to answer a query as well as the accuracy. So in the two extreme scenarios where you do a single step, in a single step scenario, you can see that the time taken is very little, around 1, and the accuracy is okay. So they did this across the various data sets. So this is a single step data set, and this is a multi-step data set across these music, hot QA, and multi-hot QA. So they found that let's say for multi-step data sets, the single step approach scores quite a low accuracy score. So EM stands for exact match, and F1 is another metric for how close the answers are. And they essentially found that they kind of showed that for the single step approach, the time taken is very little, but the accuracy is low as well. And for the multi-step approach, the accuracy is higher, but the time taken is almost 10 times, almost 10 times more. And adaptive rec, the method coded over here, essentially balances between it's able to achieve a balance of low time taken as well as high accuracy. So that's a key result. And actually this is a bit of order, maybe I just so these are some related papers. Actually these are some related papers, and the areas of improvement for the paper they mentioned is that to find better data sets, maybe exact data set, maybe they can try to generate some data sets, and also using these data sets to create a better classifier. So as you can see over here, even though scores are quite high, even though adaptive rec is an improvement from the multi-step approach, the scores itself are not really the best. So yeah. So that's essentially the end of the
Okay, let's thank Chien Hao for his presentation. We have a few minutes for questions. So again, you can think about our first lecture when Haitao went through the idea of routing, right? So we talked about a decision tree or a decision logic for deciding what type of computation or retrieval to do, whether to direct it to a data store, to a document store, answer directly. So these are all things that Chien Hao is covering again. So we've had a chance to look at some of these topics multiple times, and that's good. I mean, hopefully it's reinforcing your knowledge and clarifying and connecting some of the different concepts together again. Haitao, do you have any comments that you'd like to close the session with?
Okay, thank you very much. So I'd like to share, our recent discussion, our discussion with Professor Min about, especially when we compare adaptive RAG and smart RAG, as the student introduced about adaptive RAG, in the paper, a specific classifier is trained to make the decision, like one-time retrieval or multiple times like that. So in fact, in the context of RAG, there should be a huge space of actions. One action may respond to one decision. So if we train a specific classifier for each action, intuitively from the view of efficiency, that might not be, how to say, possible. So like Professor Min mentioned, corresponding to the huge space of actions, there might be a decision tree, right? So another straightforward method might be reinforcement learning, to dynamically determine which action to take. So that's a way of how to, comparatively understand these techniques, especially within different papers. So that's all from me. Thank you.
Any other closing comments before we end today's session?
Sure. The
Yeah,
question here.
Jonathan first.
Quite interesting to hear about just now the training method, building a data set for single pump or multiple pump. What I'm curious here is actually how to generalize this approach because it's very focused on that data set and try to look at that. You want to generalize across the broader set here? There's some.
Okay, so maybe it helps a little bit to go over what silver labels are again, just in case people didn't catch it. Did everyone understand what a silver label is? Okay, Yisong,
Noisy student.
can you elaborate? That's a one cryptic answer for people who haven't read that paper.
Yeah, sure. So I mean, we only train machine learning systems. Sometimes the bottleneck is data size. So we usually use a good enough model to help us label some of the additional data, make our data set much larger, but they are not verified by but we think these data are okay. It's like 80% accuracy. So we call it a silver as compared to golden.
Okay, did everyone hear that? So just like we can give Olympic medals, right? Your gold standard is ground truth, which is derived from human experts. Silver data can come from an annotator who might not be an expert, or it could come from an agent that's trained but not very well trained, right? So that's another way. Sometimes we call bronze data like that as well. So we call silver data maybe from non-expert human annotators, and bronze data from trained models that are not very accurate. Okay, so it just goes down and down, right? So then you can have like certificate of participation model, whatever. Okay, but the whole point is like silver labels are being produced, and then you can use these labels and then try to validate them in some way, right? So we talked about earlier a validation strategy that's going to throw away documents or queries that are too far away from their original, right? We want diverse, but not overly diverse, not psychotically diverse, right? So that's one way. Yeah, go ahead, Chien.
I haven't seen the noisy students paper, but I'm curious. If we use simple labels generated by a lousier model, wouldn't the accuracy of the better model with that straight on simple labels upper bounded by accuracy of the lousier model?
Yes. So many times you have a better model that can produce better data than you can use it. You might want to use another model for diverse sake, right? Just like what we talked about before, different models have different training regimes, different data exposure. So having that diversity, right? But I think Jonathan was also asking about the training pipeline. So can you recapitulate your question again, and maybe we can talk about it for a minute or two.
Right. No, it's actually is in this example here is actually using a very specific data and actually using the kind of a simple label kind of trainings to figure out whether it should be single pop or not pop. That is the idea, right? I'm just thinking about this. This approach is very much based on that data set here and how to generalize or because it's limited by that and limited by approach in that.
Yeah, go ahead.
Maybe if I'm asking about more generally, how do you use like this a model to like produce like your answer? I think perhaps a more general strategy would be GRPO. So it's like it's repeatedly growing the same model, but with a very small temperature. Then you have a verifiable reward, and you verify the final model answer. If it matches the reward, then you ask the model to step towards the answer. So optimize for the answer. So in that way, you can use the same model to refine its own parameters. So it's what DeepSeek used to train R1.
Another thing you can think about when you're trying to build a multi-hop data set is question generation. So just like we talked about Ksenia's part of it, where we were talking about DoctorQuery, right? So you imagine a document generating a query. So you look at that query that's generated, say it's a one hop query, right? What I'm going to do with this one hop query is mask out a section of that query and generate a filler for it. And then you can generate a filler that might generate another document, right? So many times you can do that to say, okay, the document might say something like, I think some of the questions were like, who was the president at a certain time, right? So you can say, oh, I X out that time and I generate a new time, right? Or I generate a generalization. Then I can find another document that might be a different prompt. So question generation is another area that's a little bit like query rewriting. I mean, see, these are somewhat synonyms of each other. But query and questions connote different things. Queries are usually things that you type in. Questions are natural language questions. And rewriting versus generation have different questions. So I encourage you to think about that sort of polysemous, but sort of synonymic, using Ada's terminology earlier, their relation. Okay. So with that, I think we can thank all of our speakers today. Okay, so going forward, I think the next couple of lectures are pretty different. We're going to be looking at different data sources. So we have RAG on graphs as well as multimodal information. Okay, so thanks everyone for coming. So that's it for today.